Hello everyone, welcome back to Ronnie Explains. So in this video I'm going to take you through the process of designing a circuit of a full adder, and the final circuit that you expect looks like the one on the screen. We are going to use these two hexadecimal switches to test for its working. For example, if I want to add 3 and 2, then I would click 3 and 2, then I see the result on this hexadecimal display. So very fast, let's start working it out. So I'll open this spreadsheet document, and then I would just do a quick reminder of how we used to add numbers, like normal decimal numbers. So if you have, for example, 24 plus a number like 6, so how did we use to add these two? So this is what is going to happen. So what we need to do is add 4 plus 6, which gives us 10. Then the 10 that we have, we write 0 here. So we write 0 and we carry this 1 here. And then we add 1 plus 2, and 1 plus 2 gives us 3. So at the end of the day, 24 plus 6 is equal to 30. Now, how does this work? Like, why do we write this 0 and carry this 1? Now, this is what happens basically. So 4 plus 6 is 10. So all decimal numbers are to base 10. So therefore, right here we'll be having 10, and we divide it by its base. So we write this number like this. So we divide it like this. Now, 10 goes into 10 how many times? It goes here 1 times. 1 times 10 is 10. And 10 minus 10, so that is how we used to do it. So after knowing this, what will be happening here is we'll simply write the 0, we write the remainder and carry the quotient. So the remainder in this case is 0, that's why we were writing 0 here, and we carry the quotient, which is 1, and we carry that 1 here. Now let's do it in binary. So in binary, if you have a number here, for example 1 plus 1, if you do the normal addition, 1 plus 1 is equal to 2, so you'll have the 2 here. And if you divide it by the base of a binary number is 2. So if you divide it by the base, which is 2, 2 goes into 2 how many times? It goes there 1 times. 1 times 2 is 2. And 2 minus 2 is 0. So like we said, we write the remainder, which is 0, and carry the quotient, which is 1. So then 1 plus 0 plus 0 will give us 1. So therefore in binary, 1 plus 1 is 1, 0. Now what about 1 plus 0? 1 plus 0 is simple. It is simply 1. So 1 plus 0 is 1. What about 0 plus 1? It is true for this. 0 plus 1 is the same as 1 plus 0, which is 1. So once we know this trick in addition of binary, then we can use this trick to create our adders. So we have some values here. We have A and B, and this other side we have the result, which is Y, and Y is the addition, or let me just call it sum. So here we have 0, 0, we have 0, 1, we have 1, 0, we have 1, 1. 0 plus 0 is 0, and we can also have a fourth column here called the carry out, because when we are adding, we can have some values that can be carried out. So 0 plus 0 is 0. What we carry out is nothing, carry 0. 0 plus 1 is 1, and we carry out nothing. 1 plus 0 is also 1, and we carry out 0. And 1 plus 1 is 1 plus 1, we said we write 0, and we carry out 1. So here I'll write 0, and here I'll carry out 1. Let's do a close examination of this table that I've created here. If you look at it keenly, then you will realize that the column of sum here, we have, if the inputs are the same, then we have a false value in the column of the sum. If the inputs are different, like in the case of 0 and 1 and 1 and 0, then we have true values, like in this place here. And if the inputs are the same, then again we have a false value. Now, from the knowledge of logic gates, which type of gate is that? So we realize that that one is absolutely an XOR gate. So it means that sum is implemented using an XOR gate. Now let's do a close examination of the carry out. In the carry out, you realize that the values of this carry out, the value is only true if all the inputs are 1, if all the inputs are true. That is a characteristic of a logic gate called an AND gate. So in short, the carry out values are implemented using AND gate, and the sum are implemented using XOR gate. So therefore, we have all the information that we require to implement this circuit. So I will now launch my ADDER software. So after we have launched this software, we are going to start the implementation of this, and we are going to begin by doing our setup. So I'll come to layers, instant labels and port labels have been checked. Then I come to view and set my magnetic grid to 1/8. So I will create some input switches. So I'll create IOI pin switch, and I'll have 3 of them, and I'll just reduce this a bit. So I'll name this as A, then I'll name this as B, and I'll name this as C in. So I will do the implementation of the sum by using the XOR gate, just as we saw here. So I'll create some XOR gates, and there are 2 inputs. So the first one, I'll put it there, and then I'll put another one there. So I will connect A and B to the first one and name this A XOR B. Then I will connect A XOR B to this one here, and also connect this here, which is C in. C in represents the signals from the carry out ports of each half adder, and they are being carried to the next half adder, so that cumulatively it can form a full adder circuit. So the name of this one here will be A XOR B XOR C in. Then this other side, I will put an output LED. So I'll create IO output LED and put it here. Then I'll name this as sum and connect it to that. So to view it in full mode, that's how it looks like. Now down here, I am going to do the implementation of the carry out. Now, I want to implement it in such a way that the addition of A, B, and C in can be done by picking any of these two values, any of the three values, but now in twos. For example, I can either add AB or AC in or BC in, so whichever. So it means I'm going to require 3 AND gates. So here I'm going to create gates, then AND gates in twos, and I'll create them here, 3 of them. So the first one, which is A, I'm going to combine it with B and call this as AB. Then I'm going to call this here as BC. And finally, I'm going to call this as AC in. So AB will be connected down here. So I'll add a wire segment and connect AB. Connect A to AB and also B to the same gate. Then BC in. So I'll have this B here being connected to this gate of BC in, and also C in being connected here. And AC in, so I'll have this A here being connected here, and the C in, which is a carry in, also being connected here. Then I will combine these min terms using an OR gate. So this other side, I will create a 3-input OR gate. So that will be this one here. So this will be connected here. This here will also be connected here, and then I'll also connect this one. The output of the carry out bit will be this other side. Before that, I will name this as AB or BC in or AC in. Then I will have an LED. Its LED will be somewhere here. And I can connect that and name this as carry out. So this is how the circuit of this half adder looks like. So we can test for its working, if at all it can give us the values that we are having here before proceeding to create its tester circuit. So if I just enable these ones, then I add 0 plus 0. So 0 plus 0, as you can see here, 0, 0 is just 0. So that one is that. Then 0 plus 1, so 0 plus 1 is 1, and the carry out is 0. You can see it's 1, carry out is 0. 1 plus 0 is 1. The carry out is also 0. Then 1 plus 1 is 0. The carry out is 1. Then I will come to edit, create symbol, and then I come to file, then I open new file. So I will also set my magnetic grid to 1/8 once more. Then I will create a sub-design of this half adder here. Now, how many sub-designs do I require? I require 4 sub-designs because for me to implement the addition of 4 bits, then I need to have the 4 sub-designs, where one sub-design adds and carries out to another sub-design. Now this, I'll name it as sub-design 1, like that. Then I'll name this as sub-design 2. Then I'll name this as sub-design 3 and name this as sub-design 4. So this is how it looks like. On this other side, I am going to have some things here, like I'm going to create some input switches. So I'll create IO, I-pin switch, and I'll have for A and B in each instance. For example, this one here, I'll make for A here, and then I have for B here. And then I also have another one here for A and for B, then for A and for B again. Then here also I'll have for A and for B. I'll just give them some names. But before that, we realize, because the C-in of these 3 first sub-designs will be receiving their currents from the previous sub-design. It means the C-in of the last sub-design here will be empty, and therefore I also require to give it an input switch. So I'll copy this and put it here. The name of this one here will be C-in. Like that. So I am going to put it here. Then for these other ones, I will name them from the top. Like this one here will be A1. This will be B1. This one here will be A2, and this one here will be B2. Then this will be A3, and this will be B3. And this one here will be A4, and this will be B4. Then I will have to connect all the ports. like this. And now the carry out here will be taking the signal to the carry in the next subdesign. So the carry out takes the signal to the next subdesign, and it's the same for all of them. And then I continue with the ports. I connect all these ports. Like that. Now this carry out that is remaining here, it is not being connected to any subdesign, and therefore I'll put an LED here that can store its value. So create IO output LED that can give out its value whether it's having a carry out or it doesn't have a carry out. And I'll name this as carry out. So the carry out will be connected to this carry out, and here I will have some LEDs to show me the output of these additions. So here I'll create output LED, and I will have 4 of them. So the first one is being connected to this one. The second one is being connected here. Then this should be connected here. And finally, this should be connected here. The names of these output LEDs, I can give them some names. For example, I can name this as 1. No, let me just name it as 0. Then name this as 1. Then 2. And finally 3. So this is how the subdesign of 4 merged half adders look like. And we can try and see how it works. So for now, if we add any 2 numbers here, we expect to see the value of the sum at this point, and we expect to see this line turning either red or remaining as gray, showing that it's either carrying out a signal or not carrying any signal at all, respectively. So that is how it looks like. For testing, I can activate all these input switches so that everything is activated like that. Then I'll start adding from this point. If I add this plus this, I expect to see here, if I put here 1 and also this 1, meaning putting this on and this one on, I expect to see here 0, sum of 0, but I expect to see a carry out, which is 1. Like that. Now you see I have here as 0, but I have a carry out because we can see that this here is red in color, indicating that it's passing out current to the next sub-design. If it comes to the next sub-design, because it's only 1, so 1 is being added to zeros because A3 and B3 are all zeros, then it means 1 plus 0, just as we saw here, should be having a sum of 1, as you can see, and no carry out, indicated by the gray wire, which shows that no current is passing to the next sub-design. But if we add 1 here, then we can see that this one automatically goes off because we have 1 plus 1, which gives us 0 and a carry out of 1. And that 1 is indicated by this red wire going this side, indicating that it's carrying currents to the next sub-design. And then the same way, the 1 is being added to zeros, and therefore the sum of the addition of 1 and 0 is 1, but the carry out is 0, and that is why we have this sum 1 being 1. If we add this, then we realize that this one is also going on. And the reason is because by the time we added this and this, we realized that we were having a sum of 0 but with a carry out. So a sum of 0 with a carry out, but remember, if you have a carry out and the carry out was 1, and 1 plus 1 should give us again 0, so it means that at the end of the day we have 3 values that are being added. We have 1 plus 1 plus 1. In this case, 1 plus 1 plus 1 is basically it is 3, but we are dividing it by 2. So 2 goes into 3 how many times? It goes there 1 times, and 1 times 2 is 2, and 3 minus 2 is 1, and that is why we write 1 and we carry 1. So if we write 1, which is the remainder, and we carry 1 that we carry is the quotient, and 1 that we are writing is the sum. And that is why you realize that here we are having this sum 2 as active, indicating that it is the remainder, and we have this wire as red, indicating that it's the carry out. So that's how it works, and the pattern continues up to the last sub-design. So I am also going to shrink this and keep it in one large sub-design and give it some hexadecimal switches and hexadecimal display, and then do the addition using decimal numbers. I will create its symbol, so I'll come here to edit, then create symbol. So in this space here, I'm going to create the sub-design of the full adder. So this sub-design here is actually a full adder, so I'll name it as full adder. Then I will have 2 hexadecimal switches here, this and this. Then down here I'll also create an I-pin switch that can help me to feed in the carry in signals, or to choose whether or not to feed in the carry in signals. So the name of this here is carry in. So it's going to be connected to this. So this here will be connected to this. This will be connected to this. Then this here be connected to that, and finally this will be connected to this. In essence, this hexadecimal switch here, I can name it A so that it feeds in A values. For this other one here, 0, so connecting from down here, so this here will be connected to this here, this will be connected to this will be connected to that, and finally this will be connected to this. Then on this side I can create an output LED that will be showing my whether I am having a carry out signal or not, and the name I can call it carry out. This other side I can have the display, so the hexadecimal display, and I will have it here. So this here will be connected like this, and finally the fourth port will be connected to the 0 of the hexadecimal display. To view in full mode, that's how it looks like. So I'll begin by activating everything here, then I begin the addition. So we can try out some random additions. For example, 3 plus 2 we know it should be 5, so I'll click 3 and click 2, then I get 5. If I try out 6 plus 1, so I will take it back to 0, all of them, then 6 plus 1 is 7, so this is what we have this other side. And then one last try, 9 plus 1 should be A because A is 10. Try 9 plus 1, so it's A. So that's it, guys. If you enjoyed watching this video, please give it a thumbs up. Consider subscribing for more upcoming content. I hope to see you in my next video. Thank you.